Czy już teraz chyba naprawiliśmy ten problem?
Tak?
Ponieważ to ten mikrofon powodował ten który zakłada na głowę.
Ten był włączony tutaj, jakoś tak leżał i to trzeszczenie się brało stąd, że jak się przechodziło, to...
Aha, i on był włączony, tak?
On włączony.
Dlaczego było? Myślałem, że to wchodzi w interakcję z tym. A czemu to nie działa?
Bo...
To trzeba na on.
Trzeba na on przestawić.
Na on, tak? To się zaczyna? 2 minuty?
Tak. No i masz ten... Włosy i podróży w prawo i teraz... Resztę z tym rzucać w tym Robert, też rzuć już slajdy.
Tak, patrzyłem tylko, czy mam tą prezentację. Jeszcze stream jest odpalony, kamerka jest, prezentacja jest, wszystko jest.
Jakbyś chciał kredyt coś ten, to masz
Duży wybór.
Tą kredą się pisze istotnie gorzej, więc ją zostawiamy na zwykłe zajęcie. Dobra. To bez mikrofonu, wiesz?
Nie.
Czy nas dobrze słychać?
Co mówisz?
A teraz?
Tak, nie.
Nic nie słychać?
Nie, żaden problem.
Głośny?
Co?
Nie, Rafał nigdy nic nie słyszy.
Nie, mikrofonu lepiej.
Ale to chcesz ten założyć, czy...
Ten to jakiś skomplikowany strasznie.
Nie.
Nie, to jest zbyt skomplikowane. Teraz? Nie. Teraz? W ogóle ani on, ani off nie działa. Nie działa? Nie działa.
Nie funguje.
O, teraz sobie zeszło. Nie, ale właśnie i w jedną opcję, i w drugą nie działa.
Hey, good morning, everyone. It is my great pleasure to open the final session of our conference. And our first speaker is Jacek Chyba from University of Gdańsk, who will tell us about path of pathology.
Thank you. And I would like to thank the organizers for inviting me and letting me speak about some pathological stuff. So, this is a path of pathology and it's a joint work with joint. Oh, teraz. Joint work with Rafał Filipów. So let's start by saying what is this pathology. So first, submeasure. What is a submeasure? It is a function defined on a power set of some set x, which is non-negative. We want that phi of empty set is 0, and we want this function to be increasing. And we also want it to be subadditive, which means that phi of a union is not greater than the sum of submeasures. And we say that submeasure is lower semi-continuous if it is phi of A is supremum of phi of F for all finite subsets of A. Okay. So this is the definition of lower semi-continuous submeasure. And now we have a definition what does it mean for a submeasure to be non-pathological. It is non-pathological if for every A, phi of A is equal to the supremum of mu of A, where mu's are measured, where mu is a measure dominated by phi. By mu less or equal phi, I mean that for absolutely every set B, mu of B is less or equal to phi of B. So this is non-pathological submeasure, and if it is not non-pathological, then it is pathology. So that's the pathology from the title of the talk, part of it. So we have pathological submeasures. And now, not all pathologies are the same. We can even define a degree of pathology, which says how pathological submeasure is. The degree of pathology is given by P of phi. This is supremum of all ratios phi of A divided by phi hat of A. Phi hat is this guy, the supremum of all measures. And the supremum of measures, well, this is a number, so phi of A is also some real value, we can divide them, and supremum of all those ratios is the degree of pathology. So, of course, submeasure phi is not pathological if and only if this degree is 1. Because if this degree is 1, then on phi and phi hat has to be the same, which means that phi and phi hat is equal, so the supremum of measures is equal to the submeasure. So it is non-pathological, and if it is greater than 1, then of course there is some set where these two are not the same, so submeasure is pathological. Okay, so some examples of submeasures. Every measure is a non-pathological submeasure, which is, I think, pretty simple. Another example of non-pathological submeasure is phi of A equal to the supremum of cardinality of A in the interval 2 to the n to the n plus 1 divided by the length of this interval. So this is a supremum of measures, so it is a non-pathological submeasure, and at the same time it is not a measure. So it is a simple example of non-pathological submeasures. And if you want a pathological submeasure, then we can put 0 on the empty set, 2 on the whole set, and 1 everywhere else. And for this, degree of pathology would be well, 1 if x is a singleton, but for all finite other x, the degree of pathology is 2 times cardinality of x minus 1 divided by cardinality of x, and 2 for infinite x. But that means that psi is pathological for any x which has at least 3 elements. And this is something that one can count on fingers if one would really bother to take the time to do it. But let's not. So, here, this shows that you can make a pretty simple example of pathological submeasures in only 3 elements of a set to do it. So, now that we have some examples, let's consider these notions, these definitions once again, and see that these are not the only definitions one can find of these terms in the literature, but even these that one can find, and one can find articles where these definitions are defined like on the slide. This is a very pathological definition because you can read it in like multiple ways. Like because we have like supremum of measures. Like we have here that me is a measure, but what is a measure? Do we count only countable additive measures, or do we also consider finitely additive measures? And at the same time, do we want this to check this A for every subset, or maybe for only finite subsets? And the same thing can be asked about this degree of pathology. Yeah? Do we count this phi hat by countable or finitely additive measures? And also, and one can find even different definitions, like some say that some measure is pathological if it doesn't dominate any non-zero measure, that only zero measure is smaller than phi. So there are lots of options, but thankfully we will now present a diagram which will compare all these definitions and show them in some very nice, clear way. Okay, it's not clear.
You speak mathematics when you say something is clear. Sometimes it's not.
Yeah, it's definitely not clear. So we can see that there are multiple ways you can define pathologies, and there are different options, whether we count finitely additive pathologies, finitely additive non-pathological submeasures, or maybe countably additive non-pathological submeasures is only this bottom row. We have different options for lower semi-continuous submeasures and for non-lower semi-continuous submeasures. And we have also different things if we count degree of pathology only for finite set, and we can have some pathological examples for which degree of pathology for finite set is 1. I'm not going to decipher this diagram. It just shows that there is completeness with the definitions, and it is this is a mess. So instead, we'll just stick to the lower semi-continuous submeasures and countably additive measures, and focus on why would we embark on this path of pathology. So we'll be working with ideas. So, of course, definitions may be known for everyone, but ideal by ideal I mean family of subsets, where such that it is close undertaking subsets of elements, it is close undertaking finite unions. We want that empty set belongs to ideal, the whole set doesn't. And we all want ideals to contain all finite sets. By phi, we will mean the ideal of all finite subsets of omega, and by ID, we will mean the ideal of all sets of asymptotic densities. And there is a connection between submeasures and ideals. There is a known result of Solecki that following conditions are equivalent, that I is an analytic p-ideal if and only if it is exhaustive of phi, which means that it is a family of all such sets A, such that limit of phi minus n tends to 0. And the chronologically earlier result of Mazur, that I is a sigma ideal if and only if it is equal to the family of sets with finite submeasure for some lower semi-continuous submeasure. And we can say that an ideal, analytic p-ideal or a sigma ideal is non-pathological if it can be defined by some non-pathological submeasures. And otherwise, it will be pathological ideal if all measures for which that define it are pathological, then ideal is pathology. But one can see that one can see that in practice one just needs to find a submeasure with finite degree of pathology in order to get that an ideal is non-pathological. So, one of the results that concern it is Krushack measure dichotomy. So, to introduce it, the catheter orders are ideal I is below ideal J in the catheter order if there is a function f such that for every A in I, pre-image of A belongs to J. And restriction of ideal, if we have an ideal I and a set A, I restricted to A is the family of all subsets of A belonging to I. So, the Krushack's measure dichotomy says that for analytic p-ideas, two options are possible. Either all restrictions of an idea are below ID, or there is a restriction of I which is above S. Where S is the Zalewski ideal, and it lives on a somewhat complicated space because it lives on all Klopen subsets of the Cantor space with half measure. It is an F sigma ideal, not a P ideal, but it has applications, for example, for this dichotomy, that ideals are either below ID for every restrictions, or there is a restriction which is above the Zalewski ideal. But what really interests us in this case is that the first option is equivalent to ideal being non-pathological. So ideals which are below ID are not pathological, but ideals which are above Zalewski ideal are pathological. So this is a full characterization made by Krushack of non-pathological analytic p-ideals. Which is fine. But we have also another motivation for working with pathologies, which is chronologically much earlier, and this is a Scottish book. It is hard to read what it is. Even if you know Polish, it's difficult to read what he wrote here. So maybe let's move on to see what it is about. First, some introductions of definitions. So we have this problem from the Scottish book concerns matrix summability. So we have infinite non-negative matrices we have a matrix, this is infinite matrix. We have infinite matrix. We say that it is regular if elements on the columns tend to 0, and if sums of elements, if these sums, if we count S1, S2, and so on, we want these sums to tend to 1. So matrices like this are regular, and we have, does it mean that sequence Xn, Xi is asummable? So to have asummability, we put elements of the sequence as a column, and we just use standard matrix multiplications. We will get some A1k xk, then we will get some A2k xk, and so on. And if this sequence tends to some L, then we will say that then we will say that the sequence is A summable to A. So if one would take, say, Cesaro matrix, 1, 0, Cesaro matrix, sorry. It is done in a way that on the nth row we have n elements, 1 over n, and the rest of it are 0. And then we will say take the sequence 1 minus 1, 1 minus 1, and so on. Then the multiplication will give us 1, 0, 1/3, 0, 1/5, 0, and so on. So it will mean that the sequence 1 minus 1 will be Cesaro summable to 0. Despite it, even though all elements of this sequence are far away from 0, it is Cesaro summable to 0. And one more definition. If we have a matrix A, then all subsets for which characteristic functions are A summable to 0 form an ideal which we will call a matrix ideal. So one could see that ID is an example of the matrix ideal. Cesaro matrix gives a matrix, gives us ID. Okay, so now towards the problem from the Scottish book. One more definition: if we have an ideal and a sequence xi, then xi is I converges to some n. If for every epsilon the indices I such that xi minus l are greater than epsilon belong to ID. And the problem from the Scottish book says is ID equivalent to some matrix summable method in the realm of all bounded sequences. In other words, it asks, is there a regular matrix A such that for every bounded xi, we have that ID limit xi's ID convergent to L if and only if it is A summable to L. So we want asymmetricity and ID convergence to have the same limits. Cesaro matrix is not alright for this problem because the sequence 1 minus 1 is not ID convergent to anything, while it is matrix summable to 0, so it won't solve this problem. So once again, this problem. And Mazur knew that the answer is negative for unbounded sequences, so there is no point in trying to answer it for unbounded sequences, and we have to limit it for bounded sequences. And in the commentary, you can find the newest edition of the Scottish book says that this problem remains unsolved, even the one from 2015. Okay, so there is a problem to solve. Let's see. What was known about this problem in the meantime? For example, Friday and Miller in 1991 showed that there exists a family of matrices N such that for every bounded sequence is ID convergent to L if and only if it is A summable to L for every A belonging to L. So it doesn't solve the problem yet, because the problem says we need to find one matrix A. It only says that there is some family of matrices. It was the size of continuum in the result. So if problem would be solved if this family L was made of a single matrix, but since it was a large family of matrices, it was still unproven. However, this result was later improved by Kahn and Orhan in 2007, and they said that I convergent is equal to some matrix summability method if and only if I is a matrix idea. So, hey, ID is a matrix idea. It is given by just Zama matrix. So, problem 5 has a positive answer. Kahn and Orhan answered the current problem. They show that for some, for a class of ideas, or matrix ideas, I convergence is equal to the matrix summability. So indeed, for ID, it works. They didn't know they solved this problem at the time, and it was almost a decade until anyone noticed that the problem was already solved. So now it is solved, but at the time it was unknown, and that's why the newest edition of this Scottish book is marked as a solved problem, even though it was solved a decade ago. Problem is solved, but we're problematic people, so we decided that we will try to improve this first result, for which ideas this result of Friday and Miller works. For which ideas I convergent is equivalent, for we can find a family of matrices such that A psi is I convergent if and only if it is A summable for all matrices from the family M. And the answer was that it is equivalent to the fact that I is equal to the intersection of some matrix ideas. Okay, maybe it isn't super unexpected, but there is this suspicious gap here. So it is also equivalent to the fact that every restriction of idea is below ID. So now this is something we've already seen in this talk. This is equivalent for analytic P ideas. It is the same thing as I being non-pathological. So this result of Friday-Miller problem from the Scottish book turned out to be sort of characterization of non-pathological analytic P ideas. So that was for us really interesting. Interesting enough that we decided to work on this pathology a bit more. So, because this is the full characterization for analytic P ideas, but we haven't said anything about F sigma ideas. So, what about them? So, if we have also, let's first define another class of ideas, summable ideas. We take any divergent positive series, the family of all subsets where this series converge forms called a summable idea. And for F sigma ideas, it turns out that every non-pathological F sigma ideal is an intersection of some summable ideas, and also an intersection of some matrix ideas. Unfortunately, it is still unknown if these implications can be reversed. We really like for this to be reversible, because that would mean that non-pathological F sigma ideals and non-pathological analytic P ideals would have the same characterization. Which would mean that we could generalize the whole concept of non-pathological ideas and make them completely independent of submeasures. And that would be something that I think would be cool to develop, but unfortunately it is still unknown. It is a still unknown thing. So however, this theorem has some applications that allow us to give examples of pathological F sigma ideals. A few years ago, there were some pretty strong people who thought that they don't know any pathological F sigma ideas. Nobody ever really thought about it, didn't give any examples. This theorem gives us a number of well-known examples. For example, maybe it's not to say, Solecki ideal is pathological F sigma ideal. And also ideals of graphs with finite chromatic numbers. Ideal of all graphs with finite chromatic number is also a pathological F sigma ideal. So ideal of graphs with finite chromatic numbers, well, it lives on the they are graphs that can be. Oh, I didn't change n into omega. So these are graphs which can be colored by finitely many colors in such way that no two vertices with the same color are connected. So two well-known examples. I don't know if maybe we can call them classic even, of F sigma ideals that turned out to be pathological. And this is a pretty recent results really. There was one more known construction of pathological ideas, and for a long time, all pathological ideas look somewhat similar to the one that is described here. It was constructed by Mazur, and they all depend on the construction that for every n one can find a finite set Kn and a family Sn of subsets of Kn such that Kn cannot be covered by any n subsets of Sn, and moreover, for every probability measure on Kn, one of the elements of Sn has to have probability of at least a half. So these 2 points create a pathological submeasure. Phi is a pathological submeasure where Phi is defined as the minimum number of elements of S that covers of Sn that cover A. And for example, if we do something with these submeasures Tn, then we will get a pathological measure, submeasure, and a pathological ideal. For example, we can put phi of A as the sum of 1 over n multiplied by phi n of A divided by phi n of K. Okay, so these are this is an example of a pathological ideal. Well, for non-pathological ideals, these 3 are well-known, classical, and easy to check for everyone if they remember what is a non-pathological submeasure or ideal. ID and matrix ideals are non-pathological analytic P ideals. Some of the ideals are non-pathological F sigma ideals. And for something else, one can take, for example, ED, which is the family of all subsets of omega times omega, such that for almost every vertical line, almost every vertical lines have at more cardinality of most m for some n. Okay, so these are known versions. Something more newer, more interesting is van der Waerden ideal. Van der Waerden ideal is made of all subsets that for some n do not contain any arithmetic progression of length n, and it is a non-pathological F sigma ideal. And I think it's pretty interesting to check why it is. So let's put a sketch how this submeasure works. because it uses finite version of van der Waals idea, or van der Waals theorem, that for every n there exists a number wn such that for every arithmetic progression of length wn, if we divide it into two subsets, then at least one of them has to contain an arithmetic progression of length n. And another one is the theorem of Semeredi, that for every n and delta in 0, 1, there exists a number capital N such that for any arithmetic progression of length k, at least capital N, and for every set B subset of A which has at least delta k elements, it has to contain an arithmetic progression of length n. So these two theorems are used. And with those two theorems, we construct a sequence Vn. For V0, V1, V2 is simply identity. And for greater n's, we put as Vn the maximum of W Vn minus 1 and maximum of capital N's for Vi and I over n for all i's smaller than n. With these two, we put as our submeasure the subprimes of n such that A contains an arithmetic progression of length n. To see that it is a submeasure, it is pretty clear, because if we take something that has submeasure n, then it contains arithmetic progression of length Vn. If we divide it into two, then at least one of them has to, then because it is greater than W Vn minus 1, then at least one of these two subsets has to contain an arithmetic progression of length Vn minus 1, so it has to have submeasure n minus 1, so it works. And it's also pretty clear that phi of phi is equal to the van der Waals idea, well, because Vn tends to infinity, so of course the equality holds. Okay, but the question is, we need to find a non-pathological submeasure. So is phi non-pathological? Nobody knows. This is the problem. But we didn't really, it wasn't really important for us. Because we can put a measure mi, if we take any arithmetic progression of length Vn, we can take a submeasure of this power set of A, such that mi of C is equal to n times cardinality of C divided by Vn. Mi of C is of course equal to n, the same as submeasure of A, and at the same time, mi is at most 2 times phi. And, well, maybe we shouldn't go into too much details, but it is because of this, because this Vn's are greater than all those capital N's from the Semeredi theorem. One can check that if this measure for some set, if the mi of C is greater than some natural number I, if it is greater than some natural number I, then it means that it has I over n elements of A, so that means that it needs to have, because Vn is greater than n Vi I minus n, then it means that this subset with measure greater than I has to contain an arithmetic progression of length Vi. So it needs to have some measure I. So if the measure is greater than is at least I for any natural number I, then this submeasure also has to be at least I. So in the worst case scenario, This degree of pathology will be I plus 1 over I, and this is at most 2. So the degree of pathology is at most 2, so it means that van der Waals idea is non-pathological. So we didn't even need to find, to check if this defined submeasure is non-pathological. Just we only needed to check that it has finite degree of pathology. The degree of pathology is at most 2. So it works. So van der Waals idea is a non-pathological sigma idea. A new, well, classic example, but new result that it is non-pathological. So as I said before, if we could define non-pathological ideas as something independent of non-pathological submeasures, we could find new examples of non-pathological ideas. For example, classic example is ideal of Banach density 0. It is not F sigma, it is not a P ideal, but it would be non-pathological if we allow such generalization of the definition of non-pathological ideas. And at the same time, one could even construct a non-polar non-pathological idea. Well, we needed this T equal to C assumptions to create an ideal generated by a math family that is non-pathological, but we think it's, well, we have no idea how to do it, but it's probably quite possible to construct another example of non-pathological idea that is non-moral without additional assumptions. So this shows that this notion of non-pathological ideas could be generalized, and we would like to finish with another open problem. What about Folkman idea? The Folkman idea, it is easier to say what does it mean for a set to not belong to Folkman idea. So, set doesn't belong to Folkman idea if for every L there exists a subset, a set D of cardinality N, such that all distinct sums of elements, all sums of distinct elements of D belong to A. So this is known to be an F sigma idea, this Folkman idea, and we were able to show that there is no injection such that for every A in F, its pre-image is an ID. It is impossible for any injection. However, it is still open whether it is possible for other functions. So this question is F below ID in the Kadetov order is really the question if this results holds if we remove the injection from the sentence. So this question remains open, and also of course it is a question of whether a Folkman is pathological. Because if the answer to the first question is positive, then that would of course mean that Folkman has to be pathological. So it will be, if that were the case, then we would have another nice known example of idea that would be pathological. So there are plenty of maybe other examples that of sigma ideas, as long that for which it is yet unknown whether they are pathological, as long as we don't have the full characterization of non-pathological sigma ideas. It will be interesting to check specific examples. And this is all. Thank you.
Thank you very much. Do we have any questions? Comments? Pathological or not? let us thank the speaker again. And we're resuming in half an hour.
Fajnie, że wszystko. Kiedyś pytałem Adama,
Patologiczne nie istnieją?
chyba tak. Że coś tam, że jest tak mało znanych przykładów, że to było parę lat temu.
Aha.
Także do szkoły. Tak, musieliśmy na etapie. Ja wiem, ale widzę, ale ja widziałem już parę lat.
Ja to lubię kolorową kwiatę, ale tu takich kolorów nie mam i jeszcze jakie mają te.
No to w większości ich nie rozróżnisz.
Popatrz co oni mają tutaj. Jestem zazdrosny o coś takiego.
Ej, mega fajnie.
Widzę, że kolory i jeszcze takie te, nie?
Każdy ideał przez te funkcje tam partition regular przedstawić, co nie? Bo tam jest jakiś związek, coś się da powiedzieć, że nie wiem, jak ta funkcja jest jakaś, to ona generuje patologiczny ideał, czy to bez szans. No coś takiego, no bo jakby tu się skupiałeś na tym, że tam przez te podmiary to jakaś.
Tak, to przez podmiary robiłem.
No ale to, no tak, no ale to się tam ogranicza do tych no, sigma delta generalnie.
No właśnie naszym uogólnieniem jest przez tego katetowa to dawać. Nie, żeby przez przekroje albo no przez katetowa, bo to jest równoważne w ogólności.
No można się tak jeszcze zastanawiać, nie? No, jakby nie wiem jak to, no bo tam też jest ten sam problem, że no, te reprezentacje przez te funkcje, przez te partition regular functions, to one są no, bardzo niejednoznaczne, ale przez miary też chyba nie jest. To jest, chyba też nie jest, też bardzo nie są, no więc właśnie. Więc to... No nie wiem, jakoś na sensie no, tak mi się rzuciło, że to też jest w gdańskiej tematyce, obecnie w gdańskiej tematyce, więc... No.
Tak, tak. Ale ja tymi partycznym regular się nigdy nie zajmowałem. Prędzej Rafał byłby w stanie ci coś powiedzieć, ale nie sądzę, że było jakieś powiązanie.
No, dobra, Tomek ma tyle sensu, że ta partition regular to trochę co innego robi, z tym, w sensie ona trochę o innej własności tego ideału mówi mimo wszystko.
Zostawmy uwagę, ale tam jest. Jeszcze biegniemy po tych światach, ciekawe. No nie wiem,
Mandat dostaliście?
prawie. Było blisko.
Szaleństwo.
Ja tak autentycznie kupiłem 4 pudełka, czyli 280 sztuk, ale zapłaciłem za to prawie 1000.
Czyli to nie jest wydział starszy.
Nie. Widział to szczęśliwie. Jakby mógł, to by nic nie dostał.
No teraz z fizyki ale potem właśnie opowiadał, się różniła nauka na prawie. Sam wybierałem w Polsce, ale my jesteśmy wtedy pięknym krajem, że pracownicy naukowi administracyjne. Po to mamy panie, żeby to zrobiło.
Jedna, ona jest nikum. I płacimy tyle, że...
My jesteśmy jakoś absurdalnie, powiedzcie, jakby państwo chyba, ale...
Tak. My musimy wszelkie papierki. To jest... Cud, że podłogi nie musimy wycierać, ale dojdziemy do tego jeszcze.
Ostatnio wprowadziliśmy nowy system.
Because I'm not sure which thing you're talking about. You said about the limit of infinity.
bardziej szczegółowego rozpisania.
Maybe if you have the final test.
Schemat może jest, ale w poprzednim systemie dawało się wypełnić
Because I will define by limit h to that infinity supremum over n and maybe right, it will be easier.
Kolega dostał uwagę dopasować czasownik operacyjny do efektu.
Because okay.
W swojej formie.
Go for coffee break.
Yeah.
Forma czasownika była źle, ale to
Widzieliśmy ile, że się podejmuje?
nie widziałeś. To bardzo dobrze.
Znaczy piąta. Nie jesteśmy pewni jeszcze, czy piąta, nie? Nie, bo my w Gdańsku myśleliśmy, żeby okrągłe robić. Aha. Więc może za rok będzie 6 w Kielcach, jest za 2 lata 5 w Gdańsku, czy coś. No mamy na teleskopaną numerację, że...
Nie, ale do tej pory było coś nie tak z numeracją. To Gdańsk była pierwsza.
Tak, nie wiem.
Wrocław.
Ale no była second Wrocław, a nie było first Wrocław, to już było, nie? A poza tym w Warszawie było roaming.
No tak. Ale jak tak po prostu liczyć, to...
nie, to będzie piąta, za rok będzie piąta.
Nie, no to nie będzie piąta. No.
Tak, chociaż no troszkę to dla mnie mylące jest to for w Łodzi. Tak sugeruję, że czwartek w Łodzi.
No właśnie.
Tak.
Nie do końca jest konsekwentne.
Historia jest stąd, że jak no w Gdańsku była pierwsza konferencja, to ona była Gdańsk Logic Conference po prostu. I jakoś Grigor dopisał, nie mówiąc pozostałym organizatorom do First.
No w którymś momencie dopisał, nie?
To jest taki tribut do tego, że tam chciał, żeby to było kontynuowane, wpisał i ta drobna decyzja popchnęła cały...
A wrocławska miała jakiś...
Wrocławska była sekund.
Second Wrocław, nie?
Jak już było sekund Wrocław, no to tak.
No, taka była rzeczywiście nazwa entawentrująca. Okej. Jakoś niepokoiły ten mikrofon. Te co były przyczepiane. Czy jak jest mniej osób, no to jest mniej osób, to dało radę.
Tak, myślę, że...
Nie wiem, czy tak.
Nie, to możemy zrobić bez.
Tutaj też pamiętam to żartowanie, że któryś jest lepszy, a któryś jest gorszy. Nie wiem, czy wiadomo.
Ten jest lepszy.
Dość głośno jest to nagłośnienie kręcone. Poziom tego wzmocnienia jest dość znaczny.
Tak, no to...
Ten panel jest taki... działa, ale bardzo... nie aż tak nowoczesny komputer.
Cały czas to jest pierwsza część referatu. Tak
No, pewnie tak. No, znaczy to jest osobny referat, nie?
No,
Ale
jasne.
większa część.
Okej. Próbujemy jakiś mikrofon wchodzić, czy nie?
Można. Bo no tak, mam.
Okay, so our next speaker is Dominik Kwietniak, and he will speak about Lodz problem 32. Same work as Martin Sapok with the next stop.
Okay, yeah, thank you very much for the introduction, and it's a great pleasure to be here, and it is very nice to go outside your own bubble and see some other nice mathematics, because I usually work in dynamical systems, so this was a double pleasure for me to attend this meeting. So fun. Guys in the back, I hope your eyesight is great, and video, and I also hope that you can hear me. And what I'm going to tell you about is a joint work with Konrad Beck, Eng, and Marcin Sapok. Actually, I won't present the whole story. The second part of this story will be presented by Marcin in about an hour. So, yeah, what's the problem now? So, Rufus Bowen was a mathematician, American mathematician born in 1947, and he died very young. He died in 1978 at the age of 31. So he left a lot of good mathematics, and this mathematics. He was a student. He was a student of Smale, and he studied smooth dynamical systems. And he left a lot of very interesting results. He introduced a lot of topological methods into the study of hyperbolic dynamical systems. But he also left a list of open problems. He kept a notebook in which he noted problems which were interesting to him at that time. And later on, as a part of his legacy, this notebook was digitalized, and there was a conference organized on the occasion of to celebrate the anniversary of his birthday in Vancouver, and then this notebook was popularized. It contains very nice problems, and under the entry number 32, there is this just one sentence, classify subshifts with specification. So what I'm going to tell you about is, of course, what are subshifts with specification, and I am going to tell you about the answer, partial, not yet full answer, but partial answer showing that classification in certain sense for those subshifts is impossible, which is the content of the page, which the solution, this part of the solution is presented in the preprint we wrote with Konrad, Ho, and Max. So what we are studying is symbolic dynamics. So we pick a finite set, we call this set the alphabet, and we consider the space of all two-sided sequences with entries in A. This we end up at the alphabet with the discrete topology, and because it is finite, then the A to the Z is this space with the product topology is the counter space, the compact metric space homeomorphic to the usual counter set, and we consider the shift transformation from A to Z to itself, which is now a continuous homeomorphism. It acts in this way that it takes this B-infinite sequence of symbols from the alphabet A and simply shifts it one position to the left, so that now this dot is to mark the zero coordinate. So the entries of my sequence are shifted one position to the left, and the corresponding shift to the right is the inverse of this transformation. So we have a pair which is classically called the topological dynamical system, because we have a compact metric space, a homeomorphism from this space to itself. But now this space is interesting. It's also interesting in the context of actions of groups, as we saw yesterday during Michal's talk. But in this space, the interesting objects are also subshifts. So we consider non-empty, closed, shift invariant subsets of A to the Z. So subshifts are such subsets of A to the Z which are non-empty, closed, and shift invariant, and we call those subshifts. What is interesting for any subshift is that any subshift can be described in a nice and combinatorial way, namely so we now consider the space of all possible wards. So all finite sequences with entries in A we call wards over A, and every subshift can be described using the so-called family of forbidden wards. So given any family of wards, we now can consider the family of B-infinite sequences such that no word from F appears in X. So, of course, a word appears in a sequence if we can look at some finite sequence of consecutive indices, and we will see this word, right? That's a very natural definition. What does it mean for a word to appear in a sequence? So, and now it's a actually easy exercise in the definition of the product topology, and subshift is that any subshift is determined by some family of forbidden words. For the full shift, for the whole A to the Z, the forbidden words is the empty family. We don't forbid anything, everything can appear. But imagine that I take the binary alphabet and I take a forbidden word 1, 1. So then I get a set of all sequences in which no 2 1s appear at the consecutive positions, and this will be exactly a subshift. Forbidden words are used to define the subshift, and of course every subshift then has also words which do appear in sequences from the subshift. So we see the language of the subshift. So those are all words that appear in some X in X. And now various dynamical properties of the subshifts can be described using what happens with those in the language of the subshift. So what happens with the allowed words? So specification property, so we say that the subshift has specification property if you give me any 2 words which appear in some points of the subshift. If there exists one length k, which is a number, a fixed number, such that for every 2 words which appear in the subshift, there exists a third word of length exactly k, such that I can put this third word inside my 2 words, and I will get something in the subshift. So on the picture, it means that if you have one word, and so it means that there exists a single constant k, such that if you are given, if you consider any 2 words which appear somewhere in the subshift, then you will find one sequence in the subshift and one gluing or joining word of length exactly k, such that this configuration will appear. So this is a kind of a Markov condition. So the language has finite memory. After, if you see some word, if you wait k steps, then you can see any other word. But this is weaker than the usual Markov condition, symbolic dynamics. So this is only a kind of a generalization of a Markov condition. And now look, the subshift in which we forbid 2 1s appearing in a row has this specification property. Why? Because if you are given 2 words from such subshifts, you can always put symbol 0 in between, and if those 2 words did not contain appearance of 2 1s in a row, then gluing them with a symbol 0 in between does not create 2 1s in a row anywhere. So that's a typical example of something with the specification property. So we have this family of subshifts, which is important in dynamics because it encodes a lot of hyperbolic invariant sets. So in smooth dynamics, hyperbolic systems are a large and important class of systems which is due to some structural properties the best understood among all smooth systems. And then subshift with specification, they do appear naturally as coding of those hyperbolic systems. So this is why they are interesting from the dynamical point of view. So now Now, what kind of classification we would like to see? So now the question is when two subshifts can be considered to be the same. What can you say about the natural isomorphism relation on the space of subshifts? And of course, we would like to have this equation that let me stay over the same alphabet. It doesn't matter. So those two subshifts are isomorphic if there exists phi from x to y, a homeomorphism such that this homeomorphism commutes with the shift operator shown on those subshifts. And again, this is a general definition from a theory of topological dynamical systems, this kind of topological conjugacy, but for the shift spaces, it has a special combinatorial interpretation, namely, again, you can say something about conjugacy between two subshifts if you can see if you look at them at the level of the languages. So we can imagine that we have a block map. So given some r, some radius, a map from words of length 2r plus 1 over one alphabet towards to symbols in the other alphabet, that's a block map, capital Phi. And then if you have such a block map, then you can create a map for any subshift over A. You create a map such that in order to determine the image of some B-infinite sequence, you start at the 0 position, you place the window of length 2r plus 1 in which you see the 0 symbol and r following symbols and r preceding symbols, and you apply your map phi to determine the corresponding letter in a new alphabet. And now, in order to create the B-infinite sequence as an image, you start shifting your window to the left, to the right. Each time you shift the window, your map returns you one symbol, and you can append the symbol to the sequence you are creating. And it is easy to see that this rule gives you always a continuous shift commuting map. And there is a theorem saying that actually all continuous shift commuting maps, they are obtained in this way. So you can think, well, here uniform continuity is an important observation that we
all continuous shift preserving maps are obtained this way, but between in which context? Between
even if you change alphabets, right? Now you of course you are interested in, and then you can prove also that if you have a continuous shift commuting invertible map, then its inverse is also of this form, and therefore the conclusion is that actually the set of possible conjugacies between shift spaces is always countable. Okay, because there are only countable candidates for the conjugacy map. So now again we can look at the set space of all compact non-empty subset of A to the Z. And in this subset space, we look at the space of subshifts, which are compact connected, compact non-empty subsets, which are shift invariant. Right, and this is again with the topology given by the Hausdorff metric. This will be again the what will happen. This will be a compact metric space. So what situation do we have? We have now some compact metric space, and on this compact metric space, we have a certain equivalence relation between subshifts. And now inside this space, we have even smaller subspace of subshifts with the specification property. And we can ask if it is possible to decide in any meaningful sense if two objects in this space are isomorphic or not. And this is like its descriptive set theory formalization of Bowen's problem. That we can look at this. So one of the stories which I keep telling my colleagues working in dynamical systems, which is coming from descriptive set theory, is that Borelness for people in descriptive set theory is something like countable computability. I don't know if you agree. I'm a little bit afraid to state such a thesis in front of specialists, but
this has been stated by Simon Thomas.
Okay, so
Surface thesis for mathematics.
Yeah. Okay. So I'm relieved. Thanks. So now Borelness means countable computability. So not this algorithmic computability when you need to deal with algorithms having as input finite amount of information and have to finish their work in the finitely many steps. Now you allow yourself to your information coming to you indexed by some countable ordinal, and you also allow your algorithm to perform countably many steps when you again count the steps using countable ordinals. And if you can do that, then you have and if you think about that more carefully, and if you rewrite the definition of Borel sets in terms of transfinite induction, this is what you actually get. Borel sets are exactly those sets of a given Polish metric space that, assuming that you know everything about your countable basis for the topology, you can compute them using countably many steps using this countable protocol. So a good thing for this equivalence relation we are talking about, that this is exactly countable Borel equivalence relation on some standard Borel space. So we are in the situation in which we can apply tools from descriptive set theory to somehow pinpoint the complexity of the problem of classification using the theory of the countable Borel equivalence relations. So now countable here means that all equivalence classes are at most countable subsets. Okay, so this is exactly the case here. And now we have the following very basic notion. Maybe I should use different letters. So let me take W and Z, and those are Polish metrics, Polish spaces. And we have equivalence relation E on W and equivalence relation F, capital F, on Z. And now we define the Borel reducibility notion. So WE is Borel reducible to ZF if there exists a Borel map psi from W to Z Borel such that for every object x1, x2 in W, the fact that x1 is in the relation E with x2 holds even only if the images hold in Z. So you can think of it, okay, I like to think of it in terms of recoding a problem. So we have one problem of classification in one space, and we have a Borel algorithm to recode this problem in the another space. And now, of course, if we have such a recoding, and if we can solve the problem in the image space, then we immediately can solve the problem in the source space, in the domain. So this means that if we can reduce in this sense one equivalence relation to another equivalence relation, then the first equivalence relation is at most as complicated as the second one. It might be significantly simpler, but it wouldn't be harder to resolve it than the other. So this allows us to study this partial order between equivalence relations and try to compare them, which are the most complicated ones, what are the maximal, what are the minimal elements. Let me make one extra assumption, which is unstated, but I will use it constantly from now on, and I don't want to repeat it. So let us assume that everything we talk about is non-trivial, meaning that if I'm talking about subshift with specification, I exclude the trivial 1 fixed point subshifts from that family. And if I'm talking about Polish spaces, I always talk about perfect Polish spaces. I don't want to see any isolated points or whatever, okay? So and without this assumption, I may cheat, right? So the statements, if you forget about this assumption, that I may make statements which are false in general. So now, what is the easiest equivalence relation on the Polish space? Okay, take the real numbers and take the equality, and this is the very simple equivalence relation, and now. An equivalence relation of some other Polish space is smooth if it is Borel reducible to the equality on real numbers. And what does it mean in fact? By the definition, in fact, that you can recode your problem using real numbers such that the two objects are equivalent in your sense, even only the real numbers you associated with them are equal. So smooth relations are exactly those relations for which there exists a complete Borel invariant associating one real number. And then in dynamics, I don't have time to explain more, but in dynamics, a perfect example of a classification using smooth classification is the classification of Bernoulli subshifts which is due to Ornstein theorem. All Bernoulli subsheets are classifiable by a single number, which is the entropy. And then you find the entropy of two Bernoulli subsheets, then you will know if or not they are measure theoretic conjugate or not. Another such thing is the rotation number for orientation preserving C2 smooth circle diffeomorphism. That's also a single number you can associate to them and see whether they are conjugate or not. So that's the best you can hope for. If the relation is not smooth, then no such reduction is possible. So non-smooth relations are those which are impossible to decide using countable algorithm, and they are impossible to decide by reducing even to a countable sequence of real numbers, because now the equality or any Polish metric space is Borel reducible to the equality of the reals, and nothing like a Polish space can be used to do a classification, reasonable classification. So now there is a picture for countable Borel equivalence relations on perfect Polish spaces. We have a picture in which the higher we go, the more complicated type of relations we get. So the base of this picture is those are smooth relations. Then we have hyperfinite relations. So those are relations in which each countable Borel equivalence relations in which every equivalence class is a union of equivalence classes for some finite Borel equivalence relation. And then this picture of the comparability partial order for Borel equivalence relations, countable Borel equivalence relations becomes more complicated. Namely, there are many Borel incomparable countable Borel equivalence relations above the hyperfinite level, but there is also a maximal Borel countable Borel equivalence relation, which is given by the action of the free group on two elements on the set of all colorings of the. So we let the free group on two elements to act on the set of all possible colorings of the Cayley graph of the free group on two elements. We use two colors to associate to each vertex of this Cayley graph, Cayley tree, one of those two colors, and we let the free group to translate those colorings across the Cayley graph. And this is an action of the free group on this contour space, and then we can take the countable Borel equivalence relation given by orbit equivalence, meaning the two configurations, now two colorings of the Cayley graph of the free group are equivalent, even only if they belong to the same orbit of the action. This gives you a countable Borel equivalence relation on the space of all colorings, and this countable Borel equivalence relation is known to be universal, meaning the maximally complex countable Borel equivalence relation, in the sense that any other countable Borel equivalence relation reduces to that relation.
The relation E0 is also on the picture.
E0 is it's an example of the hyperfinite relation, and this is E0 is an equivalence relation on the set of one-sided sequences of zeros and ones in which two sequences of zeros and ones are considered to be equivalent if they have the same tail. From some moment on, they are equal. So this is the relation with zero, and this is the most basic example of something which is not smooth, and it is hyperfinite because we can consider equivalence relation in which we look at the first n coordinates and we say that two sequences are equivalent if they agree on the first n coordinates, and then our relation is the union over all those. Okay, so there are some other classes which are known to be above. One of them is treeability. So a Borel equivalence relation is treeable. So now when is a Borel equivalence relation treeable? So I have an equivalence relation inside some Polish space. So this is an equivalence relation. So in particular, it is symmetric. So in particular, I can think of it as of a Borel graph. So a set of ordered pairs, symmetric set of ordered pairs. So each ordered pair gives me now an edge of a graph, and because that's a Borel graph, I can talk about a spanning forest. So of finding a graph which contains no cycles and connected components coincides with the equivalence classes. And if there is such a Borel forest for my equivalence relation, then my equivalence relation is treeable. If not, it is not. So with this lengthy introduction, I can now hope that the theorem which we have, you can now fully understand what we have proven, that the topological conjugacy on the space of all subshifts with specification over any alphabet is not treeable. So it belongs somewhere here. In particular, it is not smooth. So in the sense of not existence of Borel classification, we are done.
So treeable are done with slows?
Sorry?
So treeable are done with slows under reducibility? Or is the class of treeable relations down with slows?
Yeah. So every hyperfinite is treeable. So there is one more that they are so-called amenable. I don't want to go inside here, but it is known that every hyperfinite is amenable. Every amenable is treeable, and there are examples showing that they are treeable, not amenable, and yeah. And here is, I think, open question whether every amenable is hyperfinite.
My question is, if something is reducible to treeable, is it treeable also?
If something is reducible to treeable, yes. So, all those classes are like that, right? Something is reducible to hyperfinite. It is hyperfinite. If you are smooth, you are hyperfinite. The other way around is important, that this is not necessarily true. So now we have this theorem, which it is nice because in some sense it resolves the original question, but it asks for more, because now the question is, and we this is what we conjecture, that actually the topological conjugacy is at this maximal level of complexity, but we cannot prove it. So now, few words about a possible proof. The method we use is the following what you need to do is you need to construct a family of subshifts with specification such that there will be an action of a free group on two elements on this family by topological conjugacies. So every orbit of this action should consist of subshifts which are topologically conjugated, and this action should preserve a free probability measure. If you are able to construct such an object, and basically this is the whole lengthy construction in the proof to present, which I would need probably another hour of the construction of the family and the appropriate action, then you have theorems telling you that such an equivalence relation admitting a sub relation with this action cannot be created. And this part of the so now descriptive C theory provides you proofs and the method, but now the center of gravity of the rest of this reasoning is transferred to the dynamical system theory. Because now you know the method, you know what you want, but you need a good control over the objects you are working with to encode all this necessary information in the space of objects you are interested in. So the proof is simple to describe at the high level. Find an action of a free group on two elements by topological conjugacies on some subfamily of shifts with specification, so that this action preserves the probability measure. But the rest is quite not super hard, but still non-trivial work to do. But yeah, I think that's enough for today. Thank you very much for your attention.
We got some questions.
You mentioned this question about the red dot, that you don't know if it is as complicated as the most complicated one. But are there any known relations which are not treeable but below the red dot, for which maybe there would be a bigger hope that it would prove that it's still not reducible?
I don't know about any. I don't know. Maybe Marcin knows, but yeah, I have no clue what would be that. It is known that if you look at the topological conjugacy of all subshifts without any dynamical restrictions, that's maximal one. But the problem is that in order to encode the free group action, the proof showing that this is the maximal one uses subshifts which are dynamically very trivial. Because it's so you know it was the same question existed in the measure setting, and the first proofs were proving that measure preserving actions are not Borel, and then they are complicated. But somebody said, okay, but if you just consider measure preserving actions, then maybe the fact that they are not Borel reflects the complexity of the ergodic decomposition. So reflects the way how you can put independent pieces together in many ways, and this gives you the complexity, and showing that ergodic systems are not Borel really pinpoints the problems inside dynamics, because now they are indecomposable. And now here is a similar situation for all subshifts, because you can basically, in a clever way, very clever way, use periodic points to encode orbits of the free group, but those are like kind of independent components of the subshift. you can see this complexity. But dynamically, it is just a fixed point and a batch of periodic orbits plus something you need to have to keep it closed. But dynamically, there is nothing interesting, nothing happens. And of course, you would like to see complexity of the family of subshifts for which there exists at least one dense orbit. So to have some kind of indecomposability. For minimal subshifts, so subshifts in which all orbits are dense, shifts with specification are completely different species. I think the best what we know that it is not smooth, but
for minimal subshifts.
Yeah, but I think
of all minimal
subshifts. Yeah. So I don't think if it is known even if it goes above hyperfinite. It's the
Just if you allow the alphabets vary, is it the same translation? Or is it the same complexity?
What was the question?
If you allow alphabets to any finite alphabet, so the union over all finite alphabets. So I think yes, because it's practically yeah. If okay, I think the answer is yes. This is a guess right now.
So by yes, you mean it's not the same?
No, it is the same complexity because you can take a union of all those and say take alphabet with 2, 3, 4 elements, and then you take subshift, and then you take this increasing union. But now there is an invariant topological entropy which tells you that everything conjugated with a given subshift sits in at most that many symbols. So I don't. But okay, this is an interesting question.
Sorry, does it make sense to classify languages with specifications?
Yes, it makes sense, but it is practically if you restrict yourself to languages of subshifts, then you have the same complexity because there's a one-to-one correspondence between subshifts and languages which have two properties. One property is that they have to be downward closed, so closed with respect to taking subwords, and two-sided extendable. So if you see a word, then it should have one extension to the left and to the right. And then there is a one-to-one correspondence between languages, so actually you can put even a topology on subshifts by looking at the characteristic function of languages and consider them as points of the contour space.
Yeah, any more questions, comments? I don't see any, so let us thank the speaker again. And we resume in about 10 minutes.
Nie wiem, czy wszystko ma Księgowi zmazywać. Właściwie tak, można może
Masz redukcję?
Dlatego, no dobra, to zostanie redukcję.
Czyli to będzie
Może ci brakować kawędzi, nie?
Ale jest
jeden język nie,
Bo to pytanie jeszcze powinno być powiązane.
jest takie powiązanie, że Europa natomiast może tak, może na przykład
mam nadzieję, że nie znajdę błędu. Ja to czytałem 3 razy. No, ryzyko takiego nie da.
dosłownie intuicję, wiesz, namawiam intuicję i potem one nie ma przez te 3 razy, tak w sensie każda linia jedno potrzebuje, nie pomyliliśmy do intuicji.
Ja też to Roberto stosuję, jak się tylko zacznie tak przelatywać elastyczne, to nie, żeby jak konfiguruj trzeci.
Więc to jest
Nie, bolące.
tak ja nie wiem, druga może znajdę jakąś to jest naturalna też. Ja nie wiem,
No jest, tak.
wiem, że praca jest fajna. Jest ta druga, to jest pomiędzy. Część okej, tam mówili operatory, to szybko się kojarzy, to jest medyka zawsze jest ważna, nie wiem. Nie wiem, że pani mają
Nie ma miejsca,
a
tutaj chyba nie.
O nie, ja nie wiem.
Właśnie to jest, co to ma ale nie przebiega logika, no nie wiem, bo to później jakiś obiekt będzie się stosować. Generalnie właśnie ryzyko Nie wiem, czy to są przykłady, że się rozwiązuje, czy takie prawdziwe
To jest ta rola
Wiesz, co się stało? Jak spojrzysz na przykład musieliśmy wykręcić tę śrubkę. Jak ją wykręciliśmy, to odcisnęliśmy to znowu. Ta śrubka nam upadła. Może kobiecym okiem dostrzeżesz gdzie, bo ona gdzieś tu. Ostatni raz słyszałem, że ona leci. Nie? Tak, ale to jest na wylot.
Co wy tu patrzycie?
To jest
Trzeba to, tak? Opuścić? Czy podnieść? Czy co?
Dobrze by było, żeby to działało jak dane sali.
No czyli do jutra jeszcze masz kupę czasu. I gdzie tą śrubkę potrzebujesz? Tam na samej górze. A drabinę masz?
Nie. Mam ławkę, którą mamy sobie na podstawę na parapecie. Tak jak to wczoraj zrobiliśmy. No bo tak dobrze, że nie wkładaliśmy krzesła na ławkę.
No tak,
Krzesło, to było za niskie, postawiliśmy ławkę. Nie było, że jedna na drugą.
Nie, no ale dobra, póki nie masz śrubki, nie ma co.
Jeśli się wpływ na wniosek konkurencyjnego, były wyniki, one były wszystkie, nie jest tak. Nie ma jak jest.
Zwykła teoria przeważania, żeby znaleźć własności z dynamiki topologicznej, takie jak do teorii to się dokładnie wyważa na teorię modelową stabilności, czyli ogólnie jak się patrzy w granicę działową, to nie jest tak samo, ale to też troszeczkę bardziej z samego punktu widzenia na przykład używając teorii, to nie tak jak o tym zrobić, to było istotne, ale na przykład nie wydane, które są przykłady, które istniały w potrzebowane przez Krzyżowskiego, jak się zastosuje to, że różne pojęcia z dynamiki odpowiadają teorii modelowej, ale w tym nie jestem pewien, czy komisji nie zrobił, bo proszę. Ale no generalnie to się wpisuje w tym, że nadal jest ta odpowiedniość i szerszej klasy wtedy podobne. Jest szansa na budowanie przykładów, Więc no tak powinno zrobić w tym sensie, no nie no, ona jakoś tam leży, od czasu do czasu warto to użyć, żeby coś zrobić. Tak, tak. Mniejsza logika niż logika pierwszego rzędu, która powiedzmy tam, o ile przestrzenie typu są zerowymiarowe, to na dowolny zwarte przestrzenie, to mniejsza sytuacja.
Dzisiaj to książka Ananda, opis model, on ma i druga część, to ma dwie części, a część druga to jest
tak, tak. On właściwie jakiś wykład zaprowadził i studenci robili
on jakoś mówi o tym, że przedstawili, ale wiesz, on lubi mieć kontrowersyjne,
I'm coming more frequently.
Chyba można trochę go dalej trzymać niż tam był pierwszy referat, bo no jest głośno dość. Przynajmniej tak. Ja próbowałem przyciszyć, ale nie udało mi się aż tak bardzo, więc...
Dobra, będę trzymał.
Manualne oddalenie jest... To jest...
A zastanawiam się, czy...
Aha, właśnie. Może nie możemy, bo musimy niestety lekko się to zaminęła.
Dobra, troszkę możesz jeszcze opuścić.
Na pewno?
Tak.
Dobra.
Ale opuść i tam po sekundzie stop, nie? Pozostałe idą dobrze, ale ta się niszczy.
Nie może wybierać, to się proszę. Nie możemy też...
Przechodzimy koło nas cała.
To jest pointer, no, główny korytarz.
Okay, so our next speaker is Marcin Sabo from McGill University, and he will speak about conjugacy of pointed systems with specification.
Thank you very much. I just wanted to say it's a great pleasure to be here with you. It's a fantastic conference. Thank you for organizing it. And also thank you to Dominique for the first part for his talk. My talk is the second part, the continuation of his talk. I'll be speaking about specification property in a context which is not only symbolic, so not only for symbolic systems. And in fact, this is, before I give you the full definition of specification due to Rufus Bowen, let me maybe tell you that even though the problem 32 was stated for systems which are symbolic, the original definition was done for systems actually which are hyperbolic, so systems on manifolds. And Rufus Bowen wanted to understand the structure of so-called axiom A diffeomorphisms. These are diffeomorphisms of manifolds which look like Anosov or hyperbolic diffeomorphisms. Hyperbolic diffeomorphisms, Anosov diffeomorphisms are really great. They have fantastic properties such as stability. If you perturb them a bit, then the system doesn't change too much. And the axiom A is a wider class. There are examples. This was defined by Snail, and then people started to study axiom A diffeomorphisms. And Rufus Bowen, among other things, he proved that. He stated this definition of specification and proved that axiom A diffeomorphisms are constructed from basic blocks, such that on these basic blocks can be decomposed into fragments where there is specification. I won't go into all the details, but in particular, this was the way seeing this way shows that axiomatic homomorphisms are topologically mixed. So, and then since it seemed that every axiomatic homomorphism is decomposed into these systems with specification, and these are the basic blocks, the natural question was to classify these basic blocks of arbitrary axiomatic homomorphisms, and then it seemed hard in hyperbolic dynamics, so I think this was his motivation of the question. Can we classify that even in the symbolic? Okay. But now the definition of specification in general. So let's start with the definition of an orbit segment. An orbit segment is basically what it says. So an orbit in a dynamical system is given by a point x, which is right here, and you take an interval on the natural numbers, and you iterate the map on x with the timestamps from this interval. So it's just a fragment of the orbit of x where the times are only indexed by.
Sorry, Martin, but to be clear, what is the context exactly here? What is x?
So we have a map tau from x is a space, and we have a map tau from x to x. Okay. That's the context of dynamics in the case where we will be studying it. X will be a compact topological space, and tau will be homeomorphic. But in general, this is just for a map from a set to set. And then we look at the point x, and we look at its orbit. X is somewhere here, and then we look at this fragment of the points whose times are in the interval from A to B. Okay, and now K-space specification, this is where the name specification comes from, is just a bunch of orbit segments. But so these orbit segments, they are indexed by their times from the interval AB. But K-space specification is a bunch of these orbit segments where we require that the times between the end of one of them and the beginning of the next one is at least k. K is the parameter of the definition of the K-space specification. It's a bit technical, but let me just give you a picture. So K-space specification, we have 3 orbit segments, like I did in this picture, and then there are these red, blue, and green orbit segments. I didn't specify K or the timestamps, but this is what the specification would be, and it's K space is the distance. There is no distance, but if the index of the last point on the red segment is as a natural number, K distant from the index of the first number on the blue segment, and the same for the blue and the green. Okay, so this is a K-space specification. It doesn't seem like a natural object to study at all when you see it for the first time, but I will motivate it. Well, the full definition of specification property will motivate why we want to look at this K-space specification at all. Okay, and now we say that a specification is epsilon traced. So given an epsilon, which is supposed to be very small, and given a specification, let me maybe redraw it again. So we have these 3 orbit segments. We say that a point, single point z, y, epsilon traces the specification if at the appropriate times from the intervals on the first orbit segment, it is epsilon close to the points from the first orbit. In the times from the second orbit segment, it is epsilon close to the second orbit segment, and so on for the other ones. So here is the picture. The picture says that these points in the same columns, they are epsilon close. So here we have the first orbit segment. Here we have the second orbit segment. Here we have the last orbit segment. These are the timestamps, A1 to B1, A2 to B2, AN to BN. And this is the point Y, which is just one single point. The second row is one single orbit, but the times are the same. So A1 is the same as here, B1 is the same as here, AN and BN. And epsilon is fixed, and we want Y to be epsilon close in these timestamps. In the picture, which is, I think, the most explanatory, it looks like this. So we have these three orbit segments, the red one, the blue one, and the green one, which are fragments of the three distinct orbits, not distinct, but three orbits. And then this point, which is somehow winding around, is epsilon tracing them, meaning that it's close, it's epsilon close here. This is very small, this is very small, and this is very small. So otherwise, on the timestamps which are not in any of these intervals from A1 to B1, A2 to B2, and AN to BN, the point can do anything. We're not saying anything at all about its behavior. It's just supposed to be very close on these, in this case, three intervals to the three orbit segments. Okay? And now the full definition of specification is this. So it says that, a dynamical system X with a map tau has the specification property if for every epsilon there is a single number k depending on epsilon, k of epsilon, such that whenever we have a k-space specification, independent on how many orbit segments there might be a million of orbit segments, but as long as the times between the end of one of them and the beginning of the next one are at least k, then we can trace the whole specification by a single orbit in the appropriate time stamps. This k is needed because you see that these orbits, they are completely arbitrary. This might be very, very far away from this. But if we want the point, like say that the last point timestamp here is 100, and this is 105. Then if these points are very distant in the topological space, then what we want is that there is a jump from this point to this point in 5 time units. So if 5 might be not enough in some cases, if these points are very far away. So that's why we need to allow time to jump from one orbit segment to another orbit segment. And this depends on the epsilon. If we want to be very, very close to the orbit segment, then we might need more time to jump to another one. Okay? So that's the full definition of specification as defined by Rufus Bowen. And it's not very difficult to see that this is equivalent to the definition that Dominic gave with the interfix words. It's a small exercise. In fact, but there was just one k in this symbolic definition. That k is just k of 1/2. In symbolic dynamics, since we have an alphabet of just consisting of 0 and 1, there's two symbols where then 1/2 is enough to make sure that two digits are the same. If we treat 0, 1 as a discrete space, with distance between 0 and 1 equal to 1, then if we know that a point in this space is closer than epsilon to another, then they must be the same. So, but I won't go into more details. This is indeed equivalent. Okay, and then maybe let me just say that the system has periodic specification property. If additionally, we want this tracing orbit to be actually a periodic. So this is something that I won't need it, but just to mention it, actually go and show that in these axiomatic homomorphisms, the specification comes with this extra property that it's a periodic specification.
So tracing point X is previously was denoted by Y.
Yes, now it's Z.
But this length.
No, now it's X.
X, now it's X.
So the length of period is like specified like this exactly?
Yes, even that. That's what he showed. Okay. Now, this terminology is classical. It comes from Rufus Bowen. In fact, the terminology has somewhat evolved. And let me just mention that recently the notion resurfaced under a different name. The strong reducibility is the same. It's exactly the same, but just a different name. But strong reducibility is more studied for systems which are not necessarily Z systems, but actions of the free group, or just finitely joined actions of finitely joined groups.
Sorry, but this strong reproducibility is exactly equivalent to which property?
To this property that I just defined, but without periodic. So strong irreducibility is just another word for specification. Okay. Now specification implies transitivity. So Michal defined transitivity. Transitivity means that whenever you have, it means that you have a dense orbit, or whenever you have, for homeomorphisms on perfect spaces, whenever you have two non-empty sets, then you can move one of them to intersect the other one by some iteration of that one. The proof is quite easy. So transitivity is equivalent to the statement that whenever we have 2 points, x and y, in the space, that there is a third point and some timestamps, so that and whenever you have an epsilon given in advance, so that on time t1 m1 it's epsilon close to x, and on time m2 it's epsilon close to y. This is equivalent to this fact that for any two balls you can move one of them to the other one by some iteration. In this case, it will be m2 minus m1 many iterations of the map. And this follows very easily from specification. Let's just see a very simple proof. Right? Specification implies this version of the of transitivity. Well, just to familiarize ourselves with the notion. Well, we just look at, so we fix the epsilon and x and y, epsilon y, x, y are given, and then we want to find this point which is close to x, epsilon close to n, x on some time m1, and epsilon close to y on some time m2. So we look at x and y, x1 and x2. x1 is just x, and x2 is so we put k to be this k of epsilon, and x2 is just go back k minute times on y, and now the point is that these 2 points x1, so x1 and t to the power k of x2, which is just a fancy way to write y. This is specification, k-space specification. Yes, these are literally orbit segments. One is the orbit segment of x1, the other one is the orbit segment of x2, with the interval just being singleton of k. And now that's it. So by specification, there is a point which is epsilon tracing this orbit segment, and that's exactly what we want. Okay? So that's the easy way to see why specification is stronger than transitivity. It's also easy to see in symbolic dynamics from the definition that Dominique gave you, but this is just true in general. Okay? So that's a one-line proof. Now, just to make sure, I started what time?
45.
Perfect. Okay. So this Z has the desired property. Now, maybe to somewhat more familiarize ourselves with the specification, let us see that the full shift. So we look at not just a symbolic case. So we're going to look at the shifts x to the power z, where x is our alphabet. But in this case, I'm going to allow the alphabet not just to be a finite set, or not even merely 0 and 1, but to be just some compact space. So x is a compact space, x to the power z is again a compact space, and we look at the shift, which is just moving sequence by infinite sequences to the right or to the left, whichever you prefer. So we look at this full shift, and let's see that the full shift, so subshifts might or might not have the specification property. So symbolic systems in general, some of them do, some of them don't have the specification property. But the full shift does have the specification property. It's actually strengthening the fact that the full shift is transitive. If you just choose a generic sequence of zeros and ones, then its orbit is going to be dense. This is why the full shift has is transitive, but let's see that it has the specification property. So again, a very short proof, but just to make sure we've done some exercises with specification. So we want to prove the specification. So we want, if someone gives us, hands us the epsilon, we want to find k of epsilon, okay? But we are only, we are now in the context of the shift. So we choose k of epsilon so that if two sequences are if they agree around 0 from minus k of epsilon up to k of epsilon, then they are epsilon close in the metric of x to the power z. So k of epsilon is just this huge number, so that if two sequences are in agreement, in exact agreement on all of these digits, or not digits, entries, then they are epsilon close in this space. Okay? Such a number exists. It depends, of course, just on the metric that we put on the x to the power z, but we can quite explicitly find what this k of epsilon is. And now that's the end of the proof. So we claim that this k of epsilon works. So let's see how the specification, how this tracing point is found in the full shift. In the full shift, we have an abundance of points because we can find a point just by specifying its entries. So what we do is we take the specification, x1 on some timestamps from A1 to B1, x2 from A2 to B2, and what we do is just very simply glue them together into a single word. So this is what the full shift allows us. It allows us to build any sequence whatsoever that we want. So if we have this orbit segment here, but x is just a by infinite sequence. This is also by infinite sequence. This is also by infinite sequence. So we just glue these fragments of these by infinite sequences together into a single word, and then complete it arbitrarily to a by infinite word. And that's a perfectly well-defined b infinite word, and it works. That's how you show specification for the full shift. It doesn't depend on the space. It's also true in the symbolic case. Okay. All right. Enough proofs. Sorry for that. If This was a bit intense, but just wanted to show you how it works in action. Okay, now some terminology. So we are looking at dynamical systems. Dynamical system is a space together with a map. Typically, in topological dynamics, it's going to be a compact space with a homeomorphism. But we're going to look at pointed systems. What's a pointed system? A pointed system is a pointed system with a distinguished point x0. So we look at our space and we choose a point. It's like a constant. In a pointed transitive system, or a pointed system with specification, we want this chosen point x0 to be actually transitive, so that we want it transitive means that its orbit is dense. So we want this point not to be just to be arbitrary, but we want its orbit to be dense. And then typically, when we look at subshifts, we just specify one word, but one binding word, and look at its orbit. I mean, in general, we can just pick a point and look at its orbit closure, and this is a pointed system because we have chosen the point. So, somewhat, from some point of view, pointed systems are natural because we can just, if we have a big dynamical system, then we can form subsystems by choosing a point and then looking at its orbit closure, and this is a pointed system because we have just specified what the point was. Okay, so now maybe before this talk, let me say that when we look at conjugacy of pointed systems, so conjugacy of systems is the isomorphism, this category of dynamical systems. But in conjugacy of pointed systems, we also want the distinguished point to be mapped to the distinguished point by the conjugacy. Okay, so it's really a part of the language, constant, which is supposed to be mapped to the constant. And now, here's the fact that I won't prove, but just to connect specification and transitivity. For systems, let X be a compact space, and we want it to be homeomorphic to its Z power. So, for example, Cantor set, or the Hilbert, or anything like that. And from the point of view of Borel complexity, the conjugacy of pointed transitive X system is a system whose underlying space is homeomorphic to X. So, for example, I will be talking about Cantor system. What's a Cantor system? It's a system where the underlying topological space is the Cantor set. Hilbert cube system will be a system where the underlying topological space is the Hilbert cube. So, for X systems, the conjugacy of pointed transitive X systems has the same complexity as the conjugacy of pointed X systems with specification. Because one of these classes is larger, so this just boils down to reducing the problem of specification of transitive systems to the problem of to the conjugacy problem of for systems from transitive to those with specification. But can be done. So from our point of view in Borel complexity, specification in the pointed case, for these spaces, specification is the same as transitivity. Okay, and now Cantor systems. So Cantor system, these are the again in topological dynamics. These are one of the most basic examples of dynamical systems that people consider. Of course, subshifts are also Cantor systems, but more generally, they might be just come from a different type of homeomorphisms than shifts. And then, well, here's a picture of the Cantor set. The reason why I put it here is that I'm going to construct systems whose construction will be, well, I'm going to show you the construction of systems which will look very similarly to the ternary Cantor set. will be this same idea of ternary pattern will resurface very soon. Okay, and just the definition, it was mentioned by Michal, but let me repeat it. System is minimal if it has no proper subsystems or equivalently heteroorganisms. So minimal systems are not obvious to construct. If you want to construct a minimal system, I mean, it's easy to construct a transitive system. You just take a point and take its orbit closure. That's a transitive system, or the full shift is transitive. Even it has the specification covered. But if you want to construct a minimal system, then, well, you have to do something. And there are many ways of constructing minimal systems. I will show you one way in a minute. But before I do that, to connect it with complexity, let me just define this equivalence relation equality plus. Equality plus is an equivalence relation which is defined on sequences of real numbers. Okay? So one-sided sequences of real numbers. But we identify them if they enumerate the same set. So up to permutation, if they are injected, then up to permutation, they are the same. 0, 1, 0, 1, 0, 1 is the same as 1, 0, 1, 0, 1, 0. Although this is a silly example because the set is finite, but if you just change the numbers to distinct numbers, then you can see more interesting examples. Technically speaking, this is the so-called Friedman-Stanley jump. There's a notion of a jump within. In general, in logic, there are various types of jumps. Here, this is called the Friedman-Stanley jump of the equality, which is the somehow the relation which is not smooth. That's another example of a non-smooth equivalence relation, but it's not countable. It's not easier. Easier is much simpler, but this is also another example of something which is not smooth. But this one is still not extremely complicated. It's induced. This relation is induced by an action the group of all permutations of natural numbers. Because that's when the two sequences are the same. They are the same up to permutation. Okay. So now two results. The first one is due to Kaya, who studied this, the complexity of pointed Cantor minimal systems. And he showed that from the point of view of moral complexity, their conjugacy is exactly equality plus. Which is somewhat surprising because that's not what you would expect. I mean, it was expected to be classifiable by countable structures, so it is supposed to be some in the action, but it's actually exactly equality plus. And also, Ruin and Reinhardt showed that pointed Cantor transitive systems, they also have the same complexity. Okay, and now the promised minimal systems. So for a minimal, so first let me define periodic points. Given a point x, b infinite sequence of elements from x, and a number p, we look at per p of z. These are those times in the word which reappear periodically with period p. So you look at the b infinite sequence, and you want the position to reappear periodically in the sequence with period p. Okay? And now the pair of z is just all indexes which reappear with a certain period. And we say that the bi-infinite sequence is Toeplitz if every position is periodic. If every position reappears periodically with some period. You can construct such elements by just induction. Say that the period of 0 will be 2, and then you fill in all of the even positions, then you look at 1, and you say the period will be some other number, maybe 4, maybe 8, and you continue, and then you just make sure to fill in all of the positions. Jacobs and Kien showed, and this is one of the examples of minimal systems, that every Teplitz system is minimal. There are also other ways to construct minimal systems, but this is one which is especially simple to explain. And if you take a Teplitz element, you look at its orbit closure, then this is a minimal system. It's one way to construct a minimal system. And now I will use this construction, but in a little bit more restrictive way, and I will define what's an Oxtoby sequence. Oxtoby sequence is a very special type of a Teplitz system, except that Teplitz typically are considered as symbolic systems. These Oxtoby ones will be considered when we allow our alphabet to be counters, some compact space. Let's define an Oxtoby sequence. Fix a sequence of elements in our compact space X. So this sequence is fixed. Maybe enumerate all the rational numbers in the counters. And now the Oxtoby sequence, which will depend on this enumeration, is defined as follows. So let's do this. So I'm going to do a construction where I will be filling in some positions of a B-infinite word. I start by filling everything with blank. So this is my positions where I will be putting some elements of X, some X terms. Okay? Then divide the indices into a group of 3 and put X1 into every group of 3, put X1 into the first and the last. So here is 0, put X1 here in the first and last, here in the first and last, and so on both sides. Okay? This is the ternary pattern. Next, divide look bigger and divide everything into groups of 9. And then in every group of 9, look at the first triple and the last triple. You don't see it here, but this is the first triple. And then fill in the middle of the first triple with X2 and the middle of the last triple with X2 and so on. So this is the last triple from the negative side. And fill in these positions with X2. And then you'll see the pattern. The next thing is to divide everything into groups of 27, and then fill in my sequence is too short to see the blank spots anymore. But this is the first, and this is the last of the first to the right and first to the left groups of 27. And then we filled in this with X3, then there will be a blank somewhere here, and there will be X3 somewhere here, and similar here. There will be a blank somewhere here, and X3 somewhere here. And you do this, you continue. And then, well, if you continue, then you will get, so you can see the pattern, you do it for every n, and then at step n, you fill in with, using the point xn plus 1, the appropriate, oops, sorry, not yet. You will fill in the appropriate entries, and then you'll get a Teplitz word, right? Because that's what you're doing. You're filling in things periodically. And this will be a special type of an Oxtoby, a special type of Teplitz system, which will be minimal. Now, if you lost, don't worry, because now I'm going to talk about something completely different. No dynamics for a couple of minutes, maybe 2 minutes. So let me define an equivalence relation completely unrelated. I'm defining an equivalence relation on metrics on natural numbers. I say that two metrics on natural numbers are related with this ECS. I'm not saying what CS means for now. Maybe it means Cauchy sequences. But I'm defining, well, I'm not defining it. It was defined by, I will tell you by whom in a second. So I defined this equivalence relation by saying that the identity map from naturals to naturals extends to homeomorphism of the completions. So in a way, we have complete metric spaces, which are homeomorphic by where we have identity on fixed countable dense sets. From the point of descriptive set theory, this is a natural object to study. There's homeomorphism, but preserving, point-wise preserving a countable density. And now this ECS0 stands for the restriction of this relation where we look at where the completion is supposed to be compact and zero dimensional. So basically like a Cantor set. So we're looking at homeomorphism of Cantor set 1, but where you're in each you distinguish a countable density. Not a point, but countable density. And this was studied by Dean and Wu, who studied this equivalence relation and asked for its complexity. Well, they asked the question, is it reducible to equality? They actually posed a slightly more specific question, but this one implies the answer to their question. And now, how is this related to dynamical systems, you might ask? Well, the relation is that, first of all, conjugacy of pointed counter transitive systems is reducible to it by a very simple, which implies that we are above equality plus, because for pointed transitive systems, the conjugacy has complexity of equality plus. And here is a one-line proof, two-line proof. So if we have a pointed transitive counter system, then, so this is the counter set, we have the distinguished point, we just look at the natural numbers, we look at the orbit. And the orbit is like natural numbers, right? And we induce the metric from the counter set on this orbit. That's a metric on the natural numbers, right? And then it's very easy to see that these two metrics are see as equivalent exactly when the pointed systems are conjugate. This is basically at the top. So, well, as a consequence, we have a lower bound for the complexity. But that's not the lower bound that they asked for. They asked for the other bound, which is more complicated. And this is what we proved, that actually we proved that not only is reducible, but it's actually, from the previous argument, it implies that it's actually it's bi-reducible with equality class. And I won't tell you anything about the proof. Well, I already said a couple of words, but we need to reduce it to pointed counter minimal systems, and that's where the Upstoby sequences come into the picture. So we use these Upstoby sequences and the result of CAD. So we somehow code everything in these Upstoby sequences, and this is where the work is actually on the dynamical part to show that we have a reduction to the conjugacy of pointed counter systems. Okay, and then the last part very quickly. So we talked about counter systems, now Hilbert cube systems. So for Hilbert cube systems, people also study the complexity of pointed Hilbert cube systems, more precisely pointed transitive Hilbert cube systems. And Bruyan and Weilar asked what is the complexity of Hilbert cube pointed transitive systems. I mean, this is exactly what they wrote a paper about this, and this was one of the questions. I mean, it was the only one which was left open, and this is what I'm going to address in the last minute. Okay, so let me define turbulence. So if you've seen it, then you know it. If you haven't seen it, it's a property that that talks about these local orbits. Local orbit is indexed by two open sets, U and V. If we have a group G acting on a polar space X, we look at the identity neighborhood in the group G and an open set in the space X. And we look at those points which can be obtained from starting with this point X and making small jumps only by elements from V and still keeping you inside the neighborhood U. So this is local, meaning that you're only supposed to be locally in the space and locally in the group.
The numbers N and L are arbitrary, right?
Yes, they are the same. Yes, yes, but n is equal to n. Sorry. Arbitrary. Yes. And then we say that the group action is turbulent if every orbit is dense and meager. That's a natural property. And then these local orbits are somewhat dense, And Hjort showed that if an equivalence relation is induced by a turbulent action, this is his turbulence theory, then it's not reducible to any isomorphism of countable structures or any, action of this degree. And here's somehow the picture in a nutshell. So the conjugacy of pointed transitive Hilbert cube systems, the one that Bruggen and Wegener asked for, is bireducible with the action of, so we look at the Hilbert cube, we raise it to the power z, and we look at this full shift. It's a universal system. The Hilbert cube is a universal compact space. Now this is a universal compact system. The full shift and the full cube, and we look at its automorphism group, which is enormous. And this group acts on points in this space, so it preserves any dynamical property. In particular, it preserves the property of being transitive, so it acts on the set of transitive points. And now, well, this is the easy half of the proof. One reduction is just if you have a transitive point, then you look at its the full shift with this point as the distinguished point. And this is why one reduction works, the other one requires some. But both relations are Borel, so they were asking what's the complexity of this Borel equivalence, and it's bireducible with this. And then what we showed is that this action is actually turbulent. So in particular, it's not classifiable by countable structures, and well, it's actually very specific. It's a specific Borel turbulent equivalence relation, and well, just one word about the proof. It uses this nice infinite dimensional topology result on extension of homeomorphisms of the Hilbert. There's a general notion of Z sets, but in particular for finite sets. If you have two finite sets and a map which is moving one finite set to another pointwise by making a small epsilon distortion, then you can extend it to homeomorphism of the whole Hilbert cube, which is also making epsilon distortion at every single point. It's a quite deep result in infinite dimensional topology, which is actually exactly showing turbulence. Okay. And that's it. Thank you very much.
Thank you. Do we have any questions?
Can you go back to the previous theorem? Previous one. So, what's special about the Hilbert cube here? Can you replace it by another space?
Oh, here nothing special. It's here we just use the fact that it's maybe we use that it's the same as x is homeomorphic to x to the power z. But no, here there is nothing specific.
So you just take almost any space and you can do the same thing. And this bireducibility.
Yeah, this works for any space which is homeomorphic to its z power. Yeah. But well, since they ask only about the Hilbert cube, we just take this one.
Other questions? And the second theorem, the actual theorem. So this is
this one?
Yeah. So if you have any other space with the same property, then it's supposed to be true, like this.
I mean, we use this.
Yeah. So like the question is, if you have another space with this property, does this just?
I'm not sure if we know another space.
Okay. Okay, but still.
Yeah, I guess if there were a second one, then it would. Like maybe counter sets.
Do you need epsilon and epsilon, or it's for each epsilon there is a delta, so that if this is less than delta, this is less than epsilon? Do we probably more spaces like this?
Yeah, that probably would do. So it doesn't need to be the same. So for an epsilon downstairs, there is a delta upstairs. Yes, yeah, that should. But But even for that,
Okay, so I got turn the speaker again. And we resume in about 10 minutes.
Bo na ten jest skończony.
ciekawe. Kto to brzmi?
No, nie ma.
Nie wybierałem, ale powinny być w tym miejscu, w którym powinny być. Znaczy godzinę tam było.
To serdecznie o, nie pamiętam. Ten, który są same teraz. Ten teraz wykorzystam. Znam jest pewnie sekund. Zobaczymy. Tak, to prawda, ale zauważymy, że wiele prelegentów po prostu stało sobie tam, patrzyło razem z widowym. No, to jakby będzie tak samo, to będzie tak samo. Prezentacja jest... Ja mogę wstawić. Teraz.
O, proszę też.
Będę musiał wyjść w trakcie
Operacji.
efekt ostatniego wykładu. Znaczy to jest efekt też braku bezpośrednich przesiąków z Łodzi do Krakowa. Nie wiem. Znaczy nieznany był jeszcze wtedy, jak próbowałem bilet, to jeszcze nieznany był rozkład tutaj, a potem jak już miałem te bilety, to patrzyłem, nie było jakichś alternatyw, no jednak się wolę nie przesiadać.
Fajne to są te, co to?
Tak, ale to jakiś majątek kosztowało.
Tak?
Tak, jakieś tysiące złotych. Jakaś japońska kreda. Znaczy nie wiem jak
Nie,
te dawki, ale sama kreda jest.
Tak, kreda jest Hagoromo, to jest
No bo nie,
zarąbista.
super widać.
Tak, to
super
jest
widać.
zarąbista kreda.
Tak.
Ale
My mamy jakiś problem, bo kupujemy oczywiście z przetargu najtańszą kredę i jej nie widać na tablicy.
wiem. Znaczy ja mam prywatną swoją. Ja mam kupioną swoją.
To jest super.
Ja mam tą Hagoromo prywatnie kupioną. Też, żeby pisać.
To jest średnica taka standardowa.
Właśnie ona jest, wydaje mi się, ciut grubsza, ale...
No ja też użyłem takich oprawek prywatnie. Prywatnie, no. Prywatna oprawka do tego służbowa.
Tak. Właśnie
Znaczy, można kupować takie dla plastyku, do pasteli.
Tak. Jasne.
To są 2 miesiące temu kupowałem.
W sklepie budowlanym, lubryka do kredy.
No bo to jest ta kreda
Hagoromo, wiem,
nie?
one jest zarąbiste, to super.
Ona jest wielka i do takich oprawek, które sprzedają w papierniczych nie pasuje, więc dlatego musiałem kupić takie już półprzemysłowe. No budowlanie tam też potrzebują pomagać.
Okej, no to przewiedzę.
Robiłam się, pracowałam.
Teraz jak robimy normalnie, oczywiście 12 mm. Mogę mówić.
Super, to jest nie nawet to by było
Ale bardzo bardzo.
jak zażyć.
Ale nie mam tutoriali robić. A z Etną, bo do tego mam zadanie z różnymi rozwiązaniami, ale nie sprawdzone naczynami, więc nie próbowałam studentów, bo sama sobie robiłam rozwiązania, no ale są zadania plus rozwiązania. No niby bardzo teraz wspomina, że prowadzi rachunek prawdopodobieństwa, ale prowadzi się zupełnie inaczej, dlatego że studenci nie mieli wstępu do matematyki oraz nie mają teraz pomiary, więc niby prowadzą przedmioty probabilistyka i rachunek prawdopodobieństwa, ale jedni studenci nie jest matematyki, mają teraz pomiary i nie mieli wcześniej żadnego wcześniejszego prawdopodobieństwa, więc mam taki studium. A na drugim przedmiocie, które jest bardzo podobne, to mam studentów, którzy nie mieli wstępu do matematyki i nie mają teraz pomiary, ale za to wcześniej mieli jakieś wstępy prawdopodobieństwa, na którym nie mam pojęcia zrobili, bo my zaczynamy z matematyki. Więc niby dwa takie same przedmioty, ale kompletnie.
Ale te wszystkie przedmioty są raz w tygodniu.
Tak.
Czyli łącznie masz 5 spotkań w ciągu semestru.
W ciągu tygodnia 5.
To jest strasznie dużo. No, w sensie teraz powiedziałam, że nie można raz w tygodniu. Czyli proszę, 150 sekund na sekundę.
I tak już masz moja rzeczy.
Daje się, jak widziałeś, podobnie co
Strasznie.
Nie było, ale wydaje mi się, że
Algebrę abstrakcyjną, algebrę liniową informatykę kompletnie inaczej. Tak, to już nie zamiast
Co gorsze, jeszcze użyłem 2 razy, bo z Czesica prosili. A potem jeszcze reakcje,
no to się troszeczkę zmienia, ale
nie, to tak naprawdę proszę.
sprawia, że tak nie widać chyba jakichś kolejnych naturalnych klasów. To jest szerzyć.
No,
Czekajmy, bo środkowe reprezentowane.
Tak. Dziękuję bardzo.
Tak jest, agent.
Trzy guziki, ten zielony to jest laser. I niżej są prawo, lewo, tak?
Okay, so welcome to our final talk of this conference. My speaker is Witold Maciszewski from University of Warsaw, who will speak about counting Banach spaces C of K.
Thank you. So obviously, first of all, I would like to thank the organizers for organizing this conference and inviting me to give this talk. I apologize, I will say something about Banach spaces, but only very simple Banach spaces, spaces of continuous functions on a compact space, really valid continuous functions on a compact space. And I'm going to discuss several results from.
Do you hear?
Can you hear me? Oh, sorry. I'm trying to use this microphone. Now it's better. One more try. Is it better now? Okay. Now can you hear me? Okay, good. So I would like to discuss several results from some joint projects with this list of mathematicians. I will not read all these names here. And well, this result has spread it over something like 20 years period. And I'm going to talk about isomorphisms of Banach spaces. So, first, let me fix some notation. If we have two Banach spaces, I denote this way that these Banach spaces are isomorphic. Isomorphic meaning that there is a linear bijection between these Banach spaces, which is also a polymorphism. And standard notation, if we have a compact space, we look at the Banach space of real valued continuous functions on K, and we equip this Banach space with standard supremum norm. And I'm going to concentrate on the following very natural or fundamental question. We fix a class of compact spaces, and we want. Oh, this is one of the standard goals in mathematics. We look at the given class of objects, and we want to classify them up to isomorphism in this class. Pretty natural question. So this is a very general problem, how to classify up to isomorphism Banach spaces C of K for K from a given class of compact spaces. And actually I will look at slightly more modest challenge. I want to know how many isomorphism types of this function spaces we have. Obviously
these questions are close related. If we know the answer to problem 1, we know the answer to problem 2. And usually, when we know the answer to the problem 2, if this number of isomorphism types is small, usually this means that we have a complete list of isomorphism types. And on the other hand, if we know that the number of isomorphism type is huge, then there is very slim chance to get a complete classifications of object in this class. Okay, so let's recall some classical results well, before we go to some complete classes, one important remark. If we work with infinite compact spaces, then we know that the weight of a compact space, underlying compact space, is the same as the weight of a Banach space. Because that Banach space is a traceable space, the weight is the same as density of that Banach space. So this means that if we look at isomorphic Banach spaces, the weights of that compact spaces must be the same. And much deeper result says that if we have isomorphic Banach spaces, C of K and C of L, then also the cardinality of these compact spaces are the same. So when we look at such problems, like problem 1, problem 2, then it's natural to restrict ourselves to class of compact spaces of given weight and or given cardinality. So natural assumptions. So let me start with metrizable compact spaces, meaning that we have countable weight of that compact space. And classical results, if we have countable compact spaces, they are all metrizable, and actually we have this 100 here, it's all result of Mazurkiewicz and Sierpiński, that each such countable compact space is homomorphic to some ordinal space, or some countable ordinal. So we have very complete description of all such countable compact spaces. And when we have this, it's much easier to work with this isomorphic classification problem. And this is the result from the 60s that Mesaga and Kuczynski proved that if you have two such countable ordinal, that the corresponding Banach spaces are isomorphic within only if these ordinals are relatively close. And in particular, this means that we have exactly omega-1 isomorphism types of such function spaces for countable compact. And well, if we jump to the class of still metrizable compact spaces, but this time uncountable, then the situation is completely different. We have just one isomorphism. This is classical result of Minutin, I guess from the 50s, that for all uncountable metrizable compact spaces, the Banach spaces are the same up to isomorphism. So altogether, for this metrizable case, we have omega-1 isomorphism types of such compact spaces. So we settled the case when the weight is countable. So let's jump to the next level, to the weight omega-1. What can we say? In this case, okay, and well, we were able to prove together with Koszmier and Maciej Polski, somewhere, yeah, it's here, such that we were able to prove that for this weight omega-1, we have well, the maximum possible number of isomorphism types of function spaces, namely 2 to the power omega-1. This is maximal because, well, if we have a compact space of weight, say, kappa, we can embed this compact space as a closed subset of a Tikhonov cube of weight kappa. And we have
2 to the power kappa many closed subset of such Tikhonov cube of weight kappa. So we have only 2 to the power kappa topological types of such compact spaces. And well, actually, we have something more. We have this, we can replace this omega 1 by any uncountable regular particle. Then for such uncountable regular kappa, we have a family of 2 to the power kappa compact spaces such that the corresponding balance spaces are wise non-homomorphic. And we tried, but we couldn't solve the case of singular arguments. So this is natural interest open questions. What can we say? What's the number of this isomorphism classes, isomorphism types of compact of singular weight? This is open, and well, let me explain briefly how we construct this family. We use for this the well-known ladder system spaces. This is construction going back to the 70s, and already the time it was used in the context of function spaces. And this is very, very simple construction. So I will concentrate for simplicity on the case when kappa is omega 1. What is that ladder system space for kappa for omega 1? Well, let me draw a picture. So we look at omega 1, and what we do for each limit ordinal, we pick a sequence of non-limit ordinals, which is increasing and converges to alpha. And we look at the set of terms of this sequence. And then we define a very simple topology on omega 1. If we have, well, first we fix a set of limit, any set of limit ordinals below omega 1. And then we declare that all points outside this set S are isolated. And if we have alpha in S, then we make this sequence, this biological sequence, convergent to alpha. This is described in the form of basic neighborhoods of that point. So we have plenty of isolated points and some convergent sequences in our space. And it is very easy to check that this space is locally compact. And for our compact space, we take simply one-point compactification of this space. So this is quite simple construction, but difficult part is to prove this theorem that if we take two different sets of limit ordinals below omega 1, and these sets are essentially different in the sense that the symmetric difference of these two sets is a stationary subset of omega 1. Then the corresponding balance spaces are not isomorphic. And this is the core of that result. And once we have this, the remaining part is very easy. How can we get this 2 to the power omega 1 non-isomorphic Banach spaces for compact of this form? We simply use well-known theorem of Solvay that we can partition omega
1 into omega 1 stationary sets. And then for any subset, say A subset of omega 1, we take SA union of this S alpha or alpha in A. In this way, we have all these sets, the differences, as big as we wish. It's the differences, the symmetric differences, a stationary set. So this last step is quite easy here. Okay, so this is that general result, which says that for this class of compact of weight omega 1, without any other restriction, there is very little hope to get a complete isomorphic classification. We have too many isomorphic types, isomorphism types. Okay, and for the remaining part of my talk, I would like to present two smaller classes of compact of weight omega 1, two well-known classes of such compact spaces, for which the number, we cannot decide in ZFC what's the number of isomorphism classes. Isomorphism types. Okay. So the first class is well-known class of compact spaces associated with almost disjoint families. This time almost disjoint families in omega, set of natural numbers. So I recall the definition. And almost disjoint family, this is family consisting of infinite subset of omega, and the intersection of any two distinct members of this family is finite. Oh, well, actually here, our sets that we use were also almost disjoint. It's clear, but the point is that here we used subsets of omega 1, and now we jump to subsets of omega. And this makes a big difference. And and basically, when you have such almost disjoint family, you can associate a compact space with it, basically the same way as here. So what we do here, well, I think that I will draw a picture. So what we do here this time, so we have, well, let's imagine that this is a set of natural numbers. And we have this sets A from our almost disjoint family. So what we do, to each such set, we add one additional point outside omega. And what we do, we make similar as here, we make this sequence points from A convergent to that point. Okay? In this way, again, we obtain a local compact space. And we just add one point at infinity to make it compact. This is very classical construction. The problem is that it is associated with many different names. Rufka, Isbell, Franklin, but well, Roman Paul found out that actually the first appearance of such construction goes back to Alexandrov and Turison. First such construction appears in the memoirs of compact spaces written by Alexandrov and Turison. The point is that they work not in any almost disjoint family, but with a concrete one. Okay, and what can we say about function spaces living on such compacta? Well, first, here we have this complete construction of such compact spaces, but we can describe them using some general topological properties. Namely, a compact space is homomorphic to the space of this type. If and only if it's a separable compact, and here the staple means second counter the Dixon derivative. So first, for the first derivative, we throw away isolated points. For the second one, we throw isolated point from the first derivative. If we are left with 1 point, this is our space. But, well, as for this class of untable compact spaces, because we have this concrete description of such class of compact spaces, then it's easier to work with that concrete description. And well, it's easy observation that if we have infinite such almost disjoint family, then the weight of corresponding compact space is exactly ordinary. So if you want to concentrate of such compact space with weight omega 1, you are looking at almost disjoint families of size omega 1. Okay, so our third class is the class of such compact spaces of weight omega 1, meaning that the size of our family is omega 1. And, well, this result is, I guess, 15 years old, or something. Assuming CH, you can have 2 to the power continuum many spaces of this type in our class K3 with pairwise non-isomorphic Banach spaces C of K. So as many as possible. And well, what's behind this result? This is simple counter argument. Because, easy observations that we have 2 to the power continuum such compact spaces. And it's relatively easy to calculate if we look for this equivalence relation, isomorphism between function spaces. This equivalence class of this relation is of size continuum, at most continuum. So this is simple counting argument leading to this result. 2 to the power continuum objects and equivalence classes of size continuum. I will say something more later on this, if time allows. And if we assume Martin axiom and negation of CH, the situation is quite opposite. We have just one isomorphism type for this class of compact spaces being free. Just so it's dramatically different situation. And what's behind this result? It's relatively easy corollary to our joint result with Plebanec on triviality of so-called twisted sums of Banach space 0 and space C of K of this for weight omega 1. Again, this result was obtained using Martin's axiom negation of CH. Okay, so the last class of compact spaces that I'm going to discuss is, how much time do we have?
Over 20 minutes. 20
Oh.
minutes, something like this.
Okay, this is the class of separable compact linearly ordered spaces. Meaning that we have some set, linear order on this set, and our topology comes from, this is the topology generated by open intervals with respect to that order. And we want to have such linear ordered spaces, compact and separable. And again, we have similar situation as before. We have this general topological description of this class, but by the result of Staszewski, we also have a very complete description of this class. So we can easily work with this description. And so here it is. We start with any closed subset of the unit interval, subset K, and in this K we take any not necessarily closed subset A. And what we do, again, draw a picture. So we have this unit interval. We take some K, and inside this K we take any subset A, and we look our space underlying set. It is that K at the level 0, and on the level 1 we put points from A. So in other words, we take this K and we split to these two levels points from A. And well, we can consider on this lexicographic order, and our topology comes from this lexicographic order. It's easy to check that this is separable and compact. If we take for K the whole interval and for A this open interval from 0 to 1, and what we get is the well-known double arrow space. And maybe it's good to see what are the neighborhoods of in this topology of our. If you have point at the bottom level, what's the basic neighborhood of this point? That's, well, such an open and closed interval at this level, and at the bottom level we take the copy of this interval, but only open interval. If we take a point at the top level, this is symmetric. Here the neighborhood is the open, closed and open interval going to the right, and at the bottom level we take open copy of this interval. So you can see that on a single level we have the topology of Sorgenfrey line. Okay, and well, and Staszewski related these two things. He proved that if you have a separable compact linear ordered space, then it is order isomorphic to one of such objects. And order isomorphic obviously means that that's how the topology comes from order. It's also like homeomorphism in this way. Okay, and this allows us to work with this general class of compact spaces. And what we can prove here. So, well, I will concentrate again on subclass consisting of compacta of weight omega 1. And, well, this is almost 20 years old result that, again, assuming CH, we have the maximum possible number of isomorphism types of our function spaces, namely 2 to the power continuum. And again, this is the same counting argument. We have 2 to the power continuum objects, and the size of equivalence class is continuum. So this is relatively easy. Again, using some additional set theoretic assumption, we can get the opposite case, only one isomorphism type, but this time we need to use something stronger than just Martin axiom. Well, and to define this additional set-theoretic assumption, I need some definition. Well, we say if you work with some open interval in the real line of this open intervals, topological copy of the real line, we say that a subset of this open interval is omega-1 dense in this interval if each open subinterval intersects with A on a set of size omega-1. This is the meaning of omega-1 dense. And Baumgarten proposed the following axiom that any two omega-1 dense subsets of the real line are ordered isomorphic. And Baumgarten proved that this statement is consistent with ZSC. He, well, using force produced a model when the statement holds true, and this also follows from EFA, proper force axiom. And well, so when we assume this Baumgarten axiom, we can prove that for any two compact spaces from our class, so in separable compact linear ordered spaces with omega-1, corresponding boundary spaces are isomorphic. So very similar situation as before. How much time is left?
15 minutes.
15 minutes. Okay. So I will try to present some ideas of the proof. So first, maybe well, some corollaries of this. This is worth to mention. An easy corollary of this, this is repeated that theorem from the previous slide. So when we have this, so under the same assumption, we can prove that if we take any separable compact space of omega-1, then the corresponding function space is isomorphic with its square. Now the terminology is direct sum. And this follows very easily from the above theorem. Why? Because, well, it's a trivial observation that if you look at such direct sum of these function spaces, it can be identified with isometric identification with function spaces living on two copies of K. Okay. Discrete union of two copies of K. And well, if we work with separable compact lines of weight omega-2, these two copies again are separable compact line of weight omega-2. In this way, we can get this isomorphism for free. And why it's interesting? Because on the other hand, Kacper-Kucharski was able to construct a separable compact linear ordered space of weight continuum such that the corresponding Banach space is not isomorphic to the direct sum. So this means that if we look for the statement of that corollary, the statement is independent of CFC. Very simple statement. And if we assume CH, then by Kucharski result, this is not true. And if we assume Baumgarten axiom by this corollary, it's true. So what I am trying to say that even in Banach spaces theory, we can encounter quite simple statement that each are independent of CFC. Okay, so a few words on that counting argument. This is based on the following result. This is that estimate for the size of equivalence class of isomorphism, given class of function spaces. For a given compact space K, I denote in this way the family of all quotients, Hausdorff quotients of K, subjective images of K. And well, we use this out that if we have a separable compact space such that the size of dual space is continuum, then the equivalence class of this relation of isomorphisms as size continuum. And how can we apply this for that obvious polarity that I mentioned before, that if we assume that 2 to the power omega 1 is greater than continuum, when we have 2 to the power omega 1 spaces with pairwise non-isomorphic Banach spaces. Because the size of equivalence classes is continuum. And how can we apply this for our spaces? Well, if we look at, so suppose that we split all points from the interval. Then for any subset A here, if you look for the space I sub I, so to speak, only points from B. This is obviously a quotient of that split interval, because you can glue together all points outside A from this two levels 0 and 1. So we can look at this class of spaces for all A subset of the interval as a quotient of this one space. And we split all points. So this is the way how we can apply this theorem from this slide. And similar argument works for this compact spaces associated with almost disjunct families. Okay, so let me explain how do we use Malgafnian axiom. So for the proof of this theorem, this is first step is very natural. If we assume Malgafnian axioms, obviously we can apply the statement not only for the omega 1 dense subset of a real line, but because this unity interval here is a copy of that real line, we can apply this for omega 1 dense subset of this interval 0, 1. And then easy consequence of this Malgafnian axiom is that if we look at this our spaces, I sub A and I sub B, they must be order isomorphic. What we need for this? We have, by Baumgartner, we have this order isomorphism between A and B. Using Dedekind cuts, we can extend this to the order isomorphism between 0, open interval 0, 1, onto the interval 0, 1. And well, we can extend this to endpoints, and this immediately gives us an order isomorphism between this corresponding compact spaces. So it's very straightforward application of Malgafnian axiom. And so the key element of the proof is how to reduce this general case to that case of when we take unity interval and we split omega 1 dense set. So the remaining part of the proof is that reduction. And well, maybe I will just briefly show you some elements that we use here. So we use some properties of topological properties of separable compact lines and some isomorphic properties of corresponding function spaces. So, well, here we don't assume that we work with, we have this restriction of the weight of space, just this class of separable compact lines. So this space is K sub A. Well, simple remark, for any such K sub A, the weight of it is weight of K plus size of A. So this means that if we work with such compact of weight omega 1, this means that the size of A is exactly omega 1. Well-known property of compact of this class, very hereditary separable and hereditary Lindelof. And what's the consequence of this? If you look at the Cantor-Bendixson derivative of such spaces, and we iterate this Cantor-Bendixson derivative, it must stabilize on countable level because our space is hereditary Lindelof, so it cannot go up to omega 1. And because our space is hereditary separable, we throw away isolated points. So at each stage, we throw away countably many isolated points. So altogether, when we want to stabilize this Cantor-Bendixson derivative, we need to throw away only countably many points. So the difference is small. In particular, this property from the proposition implies that our class is hereditary. Every closed subset is again separate. Well, I need a piece of notation. If I fix a closed subset F of a compact space K, I denote in this way the subspace of continuous functions vanishing on F. And if we have a closed subset of a threshold compact space such that the difference is infinite, then this space of function vanishings on F is isomorphic to the space of function or the quotient space we identify, we look at the set F to identify one point. Okay, so also when we consider when the difference is finite, then this function space vanishing on F has the form C of M for some compact space M. This is what we need here. And important property which follows from an old result of Heath and Latzer that for each compact closed subset F of K from our class, we can factorize C of K as continuous function of that closed subset times functions vanishing on that set. This is general property of linear object spaces of such a thing. And the key lemma here, the most difficult part of the proof is that if we take any metrizable compact space and our K from our class is uncountable, then we factor out this space C of M from our C of K. This is a crucial element of our proof, and this is the most difficult part here. Well, when we combine together all these facts, we get the following corollary that if we start with compact space from our class, we take this Cantor-Bendixson derivative, look at the level when it stabilizes, then the corresponding function spaces on this K and this Cantor derivative are isomorphic. Because this the difference between these two spaces is compound. So when we look at this, we have this factorization from the first lemma. And because of that proposition, you can look at this space of function vanishing on that counterbending derivative as some function C of the form C of M, and M must be metrizable because actually this quotient space from proposition is bounded space. So we can factor it out, and this is the reason why we have this corollary. Another lemma, if we have such a separable compact line and it has no isolated points, then we can represent this as this is order isomorphic to just take, instead of any k, we take a whole interval and we split some subset of it. Okay. This is okay. So this is one of the next steps. So corollary to this, if we apply previous corollary, we can get that for if we work with uncountable separable compact lines, then we can reduce investigation of function spaces to the case when we look at just split some subset of it. Okay, and the final step of our reduction. If we have any separable compact line of weight omega 1, then the function space C of k is isomorphic to the space of the form function spaces on I sub B, where B is omega 1 dense set of B. So when we have this step, and we go back to that first observation, if we combine this, so we got our result. Okay, I guess that my time is over, so maybe I will just show you some references for this topic. Here.
Are there any questions?
I'm wondering whether you looked at the class of, classes of compact spaces which are close to metrizable, like Corson, Valdivia, of weight alpha. They are more or less.
Yes. Actually, Rondos asked a question, but how about Eberlein compact spaces? Class which is closest to metrizable, and we don't know. We tried, but the maximum, when we are talking about compact of weight omega 1, but we can show that we have omega 1 isomorphism types for Eberlein compact of such weight. But obviously, these are very natural questions for Eberlein, Corson, Valdivia.
We have a lower bound for the number of isomorphism types in the case of singular, right?
I'm not sure if we can get anything better than just using this exact bound for smaller regular cardinals below that singular kappa. So I think we cannot get anything better than this.
Okay, so let us thank the speaker again.
I have a few words to say. Okay. Yes, so on our web page we have the conference photo. Yes, so all good things at some point has to end or at exchange, so our conference is finishing. Thank you all for coming. First of all, we would like to thank our distinguished speakers. We had 15 of them with Mostowski lecture given by Sławek Zlecki, so let's thank them once again. Here is the web page. You can see slides of all or almost all talks. If you click view slides, you have access to them. In the poster section, there is a booklet of abstracts, and there will be those posters which will arrive achieving in PDF file. Probably by tomorrow, those posters will show up. We had around 90 registered passive participants. Not everybody came, but we are very grateful to all of you for coming here. Probably notice that our youngest participant is extremely undergraduate. Kuba Fela, hi Kuba. Yes. Of course, this would be not possible without a lot of work has to be done. So, we had our scientific committee with Szymon Wong, Adam Fela, Maciej Malicki, Robert Kowalski, and myself. This event couldn't happen without help of our organizers, our PhD students, Mateusz Lichtman, Agnieszka Winc, Michał Pawlikowski, Filip Roboś, who is not here, he's not a student anymore. But he had a poster and the web page is made by him. Patryk Linkowski, who is also a PhD student, Bartosz Kamiński, who is graduated just a month ago and did a lot of technical work. And Jonathan Lugosz, who is not here, but helped us a lot with bureaucracy stuff. So we are very grateful to all the support, also people who helped us during coffee breaks. They were first year students of mathematics, so we want to thank them. Our conference was once again let's go for it. Our conference was held under patronage by the Marshal of Łódź Voivodeship, by the patronage of rector of our university, and patronage of Polish scientific publishers PWN. Thanks to them, we got some books those books were in Polish, so we gave them to Polish people to present the posters. Also, we are grateful for financial support by Foundation of Łódź University of Technology, by Fortuna company, which gave us all juices which we drank for those 3 years were donated by Fortuna. Amir Healthy Sweets, which is some small family company, which donated out those big cookies with nuts right next to the coffee machine. It was very nice from their side. And mostly for Polish-speaking people, PWN prepared a special discount code, 25% discount if you are buying anything. It should be valid until end of June. If you would like to buy something, then you can use it. And hopefully see you next year on next edition of this conference. We are still setting up the details of the location. We will let you know in email once it's settled.
I wanted to say that people in Kielce agreed. Joanna.
Probably yes. We will
She
see.
called me today. It should be in Kielce.
Okay. So thank you all for coming once again, and for logic. Oh, of course, sorry, one more thing. It is important to mention that this is, we are in series of conferences. There was first in Gdańsk, second in Gdańsk there is this nice story that Grigor added first without anything settled for the second one. Just added first, and this is, I very like this one. This put it first, and this dream of series came true. So I like it. Then we had the conference in Wrocław, then in Warsaw last year, in Łódź, and yeah, and see you next year. And I did there 4 Łódź Logic conferences close. Thank you.
Thank you.